So welcome everyone, thank you all for coming. My name is Rodrigo. I'll talk about capacity planning for distributed systems. Actually, most concepts here can be used in a variety of underlying operating systems, but as my experience is limited to Linux systems, I'll stick to that. So I divided this presentation into the following sections. First, I'll try to put you in context in order for you to understand where I work and why we are using capacity planning there. We already have continuous integration and continuous testing. We have some teams that are using already DevOps and all these things, but even there, we need capacity planning, formal capacity planning for our systems. Then I'll try to show you the differences between performance monitoring and capacity planning. And I'll make a quick intro into queuing theory because most of the capacity planning theory that we are using uses queuing theory formula in order to model the systems that we use. So in the end, I'll try to put it all together and show you how we are practically using that in our systems. So I work at Universal Online, which is a content provider in Brazil. It's the largest content provider in Brazil. We have lots of consumer-oriented service like payment services, voice over IP, price comparison services. And recently we have moved into the service provider market. And that's the main reason, because I recently moved from the engineering team to the development team. So as a content and service provider in Brazil, what are our challenges? Brazil is a big country with lots of room for growth in the IT and the infrastructure market. It has grown so much in the last 10 years, but even then, we still have only 37% of our population in the internet. As a comparison, Argentina has 66% and the USA has 78%. So, excuse me. We have a very interesting scenario where the early adopters, the guys that were connecting using dial-up 10 years ago, they are moving to broadband internet access. And that creates a challenge for us because the new users are already connecting using broadband. So, for example, if we take an event, a yearly basis event like the Brazilian MTV Music Awards, we see a tenfold increase every year in the amount of users that choose high-definition video when we compare to the previous year. So we need to be ready for that. We just can't afford to not be able to serve this content in high definition for all these new users. And that is actually the good part in the sense that if we have more users, we have more audience, we have more advertisers and more money. But the main problem for us is that Brazil's economic stability is a recent scenario. It's not something, I believe that we only have stability for the last 10 years, so we still have to get some things right. We have high taxes, high interest rates. It's very hard for us to get the hardware we want or the hardware we need. And even when we can get it, it takes too long for us. You just can call a vendor and say, can you bring me a rack full of servers or a new router or a new storage systems? So we need to be ready to get things way earlier than it was normal for example, here in the US. And the infrastructure cost is much more expensive too. So how do we deal with all that? And our worst problem, I'll say that our worst weakness is that we do not have enough technically qualified professionals. Brazil has neglected technical training for the last 50 years maybe, and now no matter how much we want to pay, we just don't have these professionals to work with us. So the resulting fact is that we need to do more with the same infrastructure. We need to move away from tactical firefighting. We just can't throw more hardware at it because probably the hardware will not be available. We need to think forward And at the same time, we have to deal with several things, like when predicted traffic spikes, just like when a paparazzi takes a picture of a celebrity or something like that, or high demand events that will happen next week, or the organic growth, we need to plan our budget for the next years. As any provider or any technology company, we used to have those typical system performance metrics like CPU usage, I/O rates, memory usage, network traffic. And while these metrics are very important, they tell little for us about the current behavior of the application or the current user experience. Sometimes we have the CPU will be idle, the disks will be idle, you have plenty of bandwidth, but even then, your users will be complaining because the system is slow. So we need to move forward and start to look for what should we start to monitor in order to make sure that our users are having the best performance. So the commonly used tools like the SysStat package, which are, I would say that this is some kind of standard for any system administrator. It comes with IOStat and PStat and so on, and those bundle command line utilities like PS, TUP, uptime. And then we have time series charts, which become some kind of standard in our industry since in the late 90s, Adrian Cockcroft and Dr. Blair Zajac put those tools together in order to generate plots. So the main problem now is that people just install this package and they have no idea about how this data is collected, stored, and displayed. They just install a package and, okay, now I have monitoring. And that makes things worse as our systems grow. So what was meant to be only a way to display performance data has become some kind of holy grail. So people start to browse Cacti or Ganglia or anything like that, and trying to figure out things that these systems were not originally meant to answer those questions. And sometimes when I talk about capacity planning, people think about exporting the data from an RRD and just creating a trend line on Excel. So this is not like, things don't work like that. I mean, I wish that computer systems behaved like that, like a linear or a polynomial function. Unfortunately, that's not the case. So time series charts are really important for troubleshooting, simplistic forecasting, find trends in seasonal behavior. But in the end, people look at things like that, like a panel full of graphs, and we are natural. We try to find patterns in everything to see. We try to look at the spikes and the valleys and understand why is that, what's the relationship between those things, even when there is no relation at all. And as I said before, the fact that we don't know how this data is collected, stored, and displayed only makes things worse. So whenever we let ourselves delve into this kind of thinking about the spikes and valleys, we have to remember that correlation does not imply causation. And a spike in the user CPU that happened in the same time as a spike in the I/O rates, they may not be related, and you may just be barking at the wrong tree. I've seen people waste their time trying to figure out a relationship between two graphs, only to discover later that the problem was not even being monitored in his monitoring systems. So time series won't help us much if we want to create what-if scenarios, if we want to fully understand application behavior and identify non-obvious bottlenecks. And I guess this phrase from Dr. Neil Ginter, it summarizes the differences between performance monitoring and performance modeling. This is from a website called Guerrilla Manual Online, and he even has a book called Guerrilla Capacity Planning, which is very popular among capacity planners. So the difference between performance modeling and performance monitoring is like the difference between weather prediction and simply watching a weather vane twist in the wind. And that's what we started to discover as we started to implement metrics related to capacity planning. So what is capacity planning? What is it all about? Definitely not something new. To be honest, capacity planning predates computer systems. And when I started to study capacity planning, I just saw that most guys that were involved with mainframe were the, I would say, the masters of the science. So I started to think, can I apply the same techniques to modern distributed systems, or should I do that? Will it be feasible? Can I use the results in a practical way? And then I started to see queuing theory. And I believe that the first person that studied queuing theory in practical way was Dr. Agner Erlang. He was a Danish mathematician that invented the fields of traffic engineering and queuing theory. And he published a book in 1909 called The Theory of Probabilities and Telephone Conversations, which proved that telephone calls at random follow Poisson's law of distribution. So it was the de facto first capacity plan because it helped the Copenhagen Telephone Company to dimension its network. So in 1967, Dr. Alan Scher from MIT, he applied these concepts by using the Repairman Problem to model a time-sharing system while he was at MIT. The machine repairman model consists of a number of working machines with a repair facility with one or more repairmen. And whenever a machine breaks down, it's put in a queue for repair and is serviced as soon as any repairman becomes available. So he created an analogy between machines and jobs for computer systems, and the processor was a repairman. So he was able to model a time-sharing system with n terminals by using this analogy. And finally, Dr. Leonard Kleinrock, he wrote a book that is considered by many the Bible of queuing systems. And he created the basic principles of packet switching while at MIT. He was fundamental in the creation and the development of ARPANET. So this is the basic model of a queuing node where we have an open or closed network where the jobs come from. The difference is that in a closed network, you know exactly what is the number of terminals or what is the number of inputs to your queue. Meanwhile, at the same time, in an open network, you don't know, just like in the internet, you don't know how many terminals you have. So you have an arrival rate, which is the number of jobs that were received in the queuing node during the measured time. You have lambda, which describes the arrival rate. W for the time that a request spent in the queue, that is the time that it was in the queue before being serviced by the queuing node. And service time, which is fundamental for us because in our systems, in distributed systems, in internet systems, we don't want to have any time in the queue. We always want some node or some worker is ready to service the request. So the service time is very important for us because this is exactly the time that it took to serve that request. Finally, you have the throughput, which I explain later, and the completed tasks count, which is how many completed tasks were processed during the amount of time that we measured. So what is a queuing node? The queuing node can be a processor, it can be a disk, it can be a computer, it can be the whole system. It all depends on the level of detail that you want to have in your model. So service time, as I said before, is the time spent in processing. It can be the web server response time, the time it took to receive the request, process it, and give back to the client. It can be the total query time for a database, time spent in an I/O operation for a disk. It's basically how long it took to serve the request. Arrival rate and throughput They are the same thing if we are in a steady queue system, that is, in a system that the queue is not growing, or so we have a hits per second, queries per second, I/O per second, and that's exactly what it is. I mean, these are common terms for us. Then we have utilization, which is a no-brainer, but it is the amount of time that a queuing node is busy during the time in the time measured. So it's easy to understand it, but once you keep in mind that there are so many situations where it can be useful, it becomes indispensable. It can happen, for example, to choose between AMIs if you're using AWS, or, for example, you can use get resource usage data to calculate what is the utilization of your CPU. As an example, we have a CPU-bound HPC application running into 2-core virtualized systems. The application is instrumented so that every 10 seconds it printed the get R usage data into a log file. I guess it's, well, so it's pretty easy. In 10 seconds of wall clock time, this is the number of jobs it processed, and this is the user time and system time of that process. So we know that it's actually using only this of the processor. The other time it was dealing with memory locks or waiting for data for another process. And simply put, we get the system time plus the user time divided by the number of seconds, and we have the utilization of this process. So we have 2 cores, so we can run 3 application instances in the same server. Actually, in a practical way, we saw that it was better to run only 2, but at least it gives us an expectation. So even wrong expectations are better than no expectations at all in capacity planning. It's better to have some kind of expectation for what will happen with the system than having none at all. We have Little's law, which it's named after Professor John Little from MIT, and it demonstrates mathematically that the long-term average of requests in a stable system can be obtained by multiplying the average arrival rate by the average time a customer is spending in the system. So it can be used, for example, for you to calculate the minimum amount of spare workers in an application. So if we get a web server, for example, that is receiving an arrival rate of 120 hits per second, we need to take round-trip delay into consideration. So we run TCP dump and get the delta time between the SYN-ACK and SYN-FIN packages, plus the service time of the web server, that I will show later how we get that. And now we know that for any time, I need at least 11.31 workers ready to service in my web server. Otherwise, I may have some contention, because requests will get to the server and there will be no worker to serve it. And by substitution, you can get the utilization by using the arrival rate and the service time, but its demonstration would not fit into this presentation. In the end of the presentation, there will be references where you can see all these relationships between utilization and service time. So, putting it all together, once you discovered by studying queuing theory and capacity planning, once you discovered what metrics we needed, we started to instrument our applications so that we had this data, we could easily extract this data. So applications were changed to write service time, and even for some applications where we could not change the source code, we changed the configuration for Apache or for Nginx, so we have the time that the web server took to serve the request in the log files by using the %t directive. And whenever we can handle the performance penalty, we enable the extended status for the Apache web server. For Nginx, we have the request time. That the main difference between these two is that For Apache, it uses microseconds, while Nginx uses milliseconds. And once we have this data, we started to create some workload analysis of our systems. So we can see here, this is a web server, and we have a relationship between the service time that is written by the Apache and the throughput of the server. So we can observe the behavior of the application, and if we choose different colors based on the HTTP code of the reply, you'd see that when it reaches something like 150 requests per second, it becomes erratic and starts to serve internal server errors here. So this was real data from real servers, and we are having this behavior in production, and we didn't know about it since, as I said, it happened that the CPU is idle. There was no problem in disks or any kind of contention, and even then, sometimes our application, when it reached this throughput, it started to give errors to our users. And even more important, we just plotted the frequency by that the workload characterization happens. So we know exactly what is the workload that our server handles most of the time. If we translate this area graph to a time series chart, we would see that this happens in the morning while this happens in afternoon. And it's really rare, but sometimes it just reaches this throughput and starts to break the application. So now we know that if we monitor the throughput of the server or the service time of the server, it's more interesting for us to monitor that than CPU or disks or memory. Another example of the usage of this data is a simple tag collection data store. It's an application that we have that connects to several services, extracts tags from web pages, and stores it. So for each data operation, we've enabled a 64-bit counter for the number of calls of this method, and an average counter for the service time. The result was in a table, so we could see that what's the number of what's the call count of each method, and what is the service time for each method. But once we plot it, it becomes clear for us where our developers should put attention, which are the methods that they should look for, because it has the worst service time and that are called so many times. And finally, we get to modeling, which is, I would say that this is the main reason that we started to study capacity planning. So modeling is an abstraction of a complex system. It allows us to observe phenomena that cannot be easily replicated. And it's important to note that models come from God, data comes from the devil. We should be aware that the model has its limitations, and even if you can do your best, a model will not be the same as the original. So how do we do that? We create a system of queuing nodes where we receive requests from clients and we reply to it. So in this case, it's a simple LAMP stack with a web server, an application, and a database. And we wanted to know, for example, what would happen if we added a cache in front of the system. So now we know that static requests will not pass to the web server, so probably the arrival rate of the web server will decrease, while the average service time for the web server will increase. And we want to know what is the impact of this in the system, for example. This is the kind of things that we are using queuing models to solve. We are using PDKey, which Originally it was written in C, and then it was ported to Perl, and now I believe that it has bindings for most languages. I know at least R, Python, and Java. It analytically solves queuing network models of computer and manufacturing systems, data networks, etc. And you just write it in conventional programming languages. So you can create, these are some of the functions of the model. We are currently using Perl because we have some professionals that are good Perl programmers. So you can create a node which defines a queuing center. You can create open or closed networks that are traffic streams into that circuit. And you can set the demand for each of your queuing nodes. So this is a real example. We measured the service time for each of these components of our system, and we have the arrival rate, the average arrival rate for our server. So we create the nodes by using the create node function, and it creates for us, when we solve the queuing equation, it generates a report which tells us what is the number of clients in the system, the minimum number that is always connected to the systems, the mean throughput of our service, the response time of our service, what's the stretch factor in this response time. And we get here a bound analysis that tells us what is the maximum throughput and what is the minimum response time for my system. So I'll never have a response with less than that. And if I get to this number of requests per second, some component of my queuing system will saturate and the system will come to a halt. Or not to a halt, but probably you start to have some contention for the requests of my clients. I can even increase artificially the service time of only one of my components and understand what will be the behavior of the whole system by using PDKey. So here I started to increase the service time for the database service until a point where I had saturation. This is the point where the system just started to have contention. But now I understand that my database can't be slower than that. So it becomes pretty easier for us to predict when I'll have a problem in my system. So another thing that we are doing, and we are borrowing this from our user experience guys, is the CBMG, that is a customer behavior model graph. We are doing the complete makeover of a web collaborative portal. So we are moving from a commercial off-the-shelf application to a fully customized in-house solution. So how can I benchmark that? How can I know how can I know what will be the behavior of the new application if I just can't replay the log files from the original system to the new system? We are using CBMG. We had a program that analyzed the session logs and created a graph of the user behavior by plotting what's the probability of the request from moving from one node of the graph to the other. So this is not real data because I was not allowed to bring it, but the result is something like this. You have several nodes of your application, and the current probability of the user going from one point to the other. So we can get this data, and now we can understand what will be the number of calls for certain parts of my system based on the throughput. So now we can mimic the user behavior in the newly developed system. The new application was instrumented, so we knew the service time for every method, and each node in CBMG is mapped to the application methods it is related, so it becomes pretty easy for us to understand what is what's the performance that I need for every node of my system. These are the references that I told you. This is a paper that is applied specifically to web servers, And this is a paper that is a primer about queuing theory that can help you understand what we are doing there. The Analyzing Computer System Performance with PDKey by Neil Ginter. It's the book that fully describes how you can use the PDKey model. Even if you're not a pro shop, you can use this book to understand how these models work. And finally, we have the Computer Measurement Group Public Proceedings. It's a group dedicated to the study of capacity planning, and there are lots of it's for free. You can just access it and get those papers for you. Well, I guess I was much faster than I expected, but thanks for attending. If you have any questions, feel free.
I've never studied queuing theory, so I don't know if this is a stupid question, but you've got a lot of constants in that formula, like service time and arrival rate and things like that.
Mm-hmm.
And I'm wondering if the you were just using a constant, which presumably is an average of some kind. But
yes,
the
it is.
Distribution of service times, like mostly it takes a millisecond, but sometimes it takes 1200.
Mm-hmm.
Or mostly the round trip time is 50 milliseconds, but sometimes it's 1400. And was the graph like this or like this? But does that matter in queuing theory? Does it change the results significantly?
Well, actually, no. I mean, I'd have to I don't know even if I could explain you exactly what's all the math behind this theory here, but in our tests we see that the models are pretty much efficient when we apply this data to production systems. So what I can tell you is that despite the fact that we are using arrival rates averages for the service time or for the arrival rates, when we see that when we see the result and compare to a real system, it makes sense. It's not something that, obviously, as I told before, we prefer to have a wrong expectation than have no expectation at all. We prefer to get frustrated and say, oh, our model didn't work, than just do some wild guessing about how the system will behave. So I would say that try it for yourself and see the results, and please share it with me if you can.
I was wondering if you ran any particular problems trying to figure out when you did service time as a function of the arrival rate. I've tried to do that in the past and failed for the most part because I think there's several layers of caching going on and things like continuous deployment constantly change the equation. Was there any particular metrics? Was it just clear in that graph you didn't have to do much filtering, or was there specific things that came up?
You mean, let me...
Things like that.
Oh, okay.
Because I've tried to run stuff like that, and I found with the more hits we get, our service time goes down because better cache hit ratio and stuff like that. So I've actually had trouble finding any breaking points or clear patterns.
This graph is not a standard. I mean, every application will have a different pattern. I brought this example because it's a good example that shows that we didn't have this kind of behavior that you're describing. We had increase in the service time as the throughput increased to a point where the application simply exploded.
So there was no filtering you had to do or taking out certain types of requests or cache requests to come to that result?
No, because in that case it was a really kind of simple application. It was only web server, and we used the Apache service time data in order to plot this graph.
Okay.
There was no caching in Apache or in other system in front of it, so we had the let's say the raw requests getting to the server. Okay. So in this was the result, but obviously it varies depending on the system that you're graphing. The results can be completely different.
Okay, thank you.
Well, thank you.